back to another video. So the last video I did was discussing derivatives, right? Finding the function that describes the slope of another function. But today what we're going to do is we're going to use derivatives in a very useful way. We're going to use it to find minimums and maximums of a function. So think of a time where you've had to do that in math. Now, if you're going into calculus, that means you're probably taking at least some pre-calc and maybe some algebra, and this may seem very useful because you may remember, let's take some sort of parabola, for example. A lot of times, typically in optimization or in projectile motion, you're going to have, at some point, having to find some maximum of some function. It may not always be a parabola here. Sometimes it may be something like a cubic or something. In that case, you're finding local maximum or local minimum. But either way, the process usually involves you creating some sort of function and then plugging it into your graphing calculator and then using the tools on that calculator to find the maximum. But what we can do with our knowledge now of how derivatives work is that we can use the fact that maximums on a non-closed domain will occur. I keep saying maximums. It's maximums or minimums will occur when the tangent to that function is flat. That means it's equal to 0. So the question, where do relative maxes occur? What you want to think to yourself is, where is the slope or derivative equal to 0? Now this term relative max or min, I keep saying maxes. It's maxes or minimums. It doesn't really matter, right? Because if you have some parabola, maybe it's facing up, this is the minimum down here, the slope is still 0. So what I should be saying is relative extrema. Extrema basically represents minimums or maximums. But the word relative may be throwing you off because that's something you never heard. That basically covers both local min and maxes and absolute min or maxes. Right, because sometimes if you have something like a cubic function, there is no absolute max or min here, right? Because this one goes up forever, it'll always keep getting bigger and bigger, and it'll always go down because it'll get smaller and smaller. But we have local minimum maxes right here. So it's kind of just a blanket term. Either way, maxes on an open domain, min or maxes on an open domain will be when the slope is equal to 0. And I say open domain because there are some exceptions, and the first one is when you have a closed domain. Let me kind of denote this section better. This is the exceptions. So one exception is when you have a closed domain. And the reason that there's an exception on closed domain is because let's take some basic just line on a closed domain. So that means we have these filled in circles at each end. It's something like this. This does have maximum mins. Here's one max. Here's the other. You know, they're kind of just right there. It seems kind of non-intuitive, but these are the maxes on the closed domain. And notice, the derivative does exist there because it's inclusive. It would be like, maybe this is like -1 over here, and this is 3, 1 to 3. We would look on the slopes on that closed domain too. So the slope does exist here, but it's not 0. So that's why it's an exception. We're not going to worry about this. What you'll learn in your calc class is that any function on a closed domain will always have a extreme max and min, or absolute max and min. The other exception is kind of different. So let's look at a function here. Let's look at the cubic function. Y equals x cubed. Here it is. When is this function's derivative equal to 0? May not seem intuitive at first, but it's going to be right here, right? And that obviously isn't a maximum. So this kind of shows a key fact about finding mins and maxes using the derivative. You have to look for how the function increases and decreases before and after. So notice how before the function is kind of going up, going up, going up, going up, going up, going up, going up. And then it reaches that zero, it reaches that horizontal, but then it keeps going up. So this kind of shows that the derivative, or the slope, must change signs. Right, and that makes sense, because if you have some extrema, we can't have a situation where it just keeps going up. That's not a min or a max. It has to go up to down, or down to up. When I say derivative is positive or negative, that should resonate in your mind as when the function is increasing or decreasing. So those are just the two exceptions. We'll go over some examples. I know I haven't made it as clear as I kind of wanted to, but we'll start easy. So the first function we have here is f of x is equal to negative x squared plus 4x plus 1. And what we're going to do is we're going to find the max. Now notice there's no closed domain here, and I'm not specifying whether it's a local max or an absolute maximum, because we're going to be able to find that out by just using the derivative. So the maximum of a parabola is pretty easy, actually, because it's just where the vertex is, right? That makes sense. And we actually do have a formula that we can use for that. It's minus b over 2a. So what you can do is you can just plug in b, which is going to be minus 4, or b is just going to be 4, but multiplied by negative 1 is going to be negative 4. Our a value is going to be negative 1, so 2 times negative 1 is just negative 2. Negative 4 over negative 2 is just equal to 2. So we know the maximum occurs at x equals 2. And then what we can do is we can just plug 2 back into the function. We get 2 squared is 4. Negative 4 plus 4 times 2 is 8 plus 1. 8 minus 4 is 4 plus 1 is equal to 5. So the maximum here would be at 2 comma 5. And that's easy enough. But you can actually use the derivative as well, because we know at a maximum the derivative is 0. So what's the derivative of this function? Well, if you remember your derivative rules from last time, it's just going to be minus 2x plus 4. And we want to find out when this is equal to 0. So what we're going to do is just rewrite it. Negative 2x plus 4 is equal to 0, and then we're just going to solve for x. First thing you can do is add 2x to both sides. 4 is equal to 2x, divide both sides by 2. X is equal to 2. So we know some sort of extrema happens at 2. Something happens at 2. It's not guaranteed, actually, until we really look at it more. So what we're going to do is we're going to make a chart. And what we're going to do is we're going to put in the key points where the derivative is 0. So the only one we have in this case is 2. So we have our x values on the top, and then we have the derivative values on the bottom. So we know the derivative at 2 is actually just going to be 0. So from here, what you're going to do is you're going to plug in values that are less than 1 by doing it to the left of this 2. And then we're going to do values to the right of 2 that are greater than 2. And what we're going to see is we're going to see the signs that occur in the derivative. So let's give an example. So let's do a number like 1. What we're going to do is we're going to plug that 1 in to negative 2x plus 4. So what happens when you plug 1, in for x in the derivative? Well, negative 2 times 1 is negative 2. Negative 2 plus 4 is just going to be 2. So the derivative will be 2. But really, we don't need to know what the exact number is. All we need to know is that it's positive. So from that, what we know is that before x is equal to 2, the function is just increasing. The slope is always going to be positive until it reaches 2, then it's going to be 0. And then we can plug in a number like to the greater than 2, which we put in the right, like 3. Plug 3 into the derivative, you get negative 6 plus 4, that's going to be negative 2. But all we really need to know is that it's negative. For any value that's greater than 2, the derivative is going to be negative, which means the function is going to be decreasing. So what we see is we have the function increasing, increasing, increasing until 2, then it hits 0, and then it goes back down. When it goes from positive to 0 to negative, that means this is going to be a maximum. So we know some sort of maximum occurs at 2. And what we can say, because we now know the general shape of it is just this upside down parabola, we can say this is an absolute max. But don't worry about that for now, because a lot of times you're going to have functions that are a lot weirder than just, normal quadratics or cubics or stuff like that. So just know for now there's a max at 2. Max at 2. And then you can kind of do the same process as before, where you plug this back into the original function, and we know that you get 5. So the maximum is at 2, 5, or you can write it out as there is an, just say maximum for now. We're not going to worry about absolute. We'll just say max of 5 at x is equal to 2. So that seems easy enough. It may seem a little unnecessary for a function that's this simple, but let's go over an example here of a cubic. F of x is equal to x cubed minus 6x squared plus 15. Now for this one, we don't really know what the function looks like, and we don't have a quick and easy way to just get the max and minimums. So what we're going to do is we're going to take the derivative. F prime of x is going to be equal to 3x squared minus 12x. The 15 is just a constant, so we can ignore that for now. And then again, we're going to take our derivative, we're going to set it equal to 0. Okay, so the first thing I'm going to do here is I'm going to divide both sides by 3. We're going to add x squared minus 4x is equal to 0. And then we can just pull out an x. And this is an important form to keep it in. So now we know that the derivative is 0 at x equals 0 and 4. And then we're just going to go back in. We're going to make our chart again. So we're going to list our points where we know the derivative is 0. We're going to put zeros below them. And then we're just going to keep testing points. So we can try -1 here, maybe like 2 here, and then a 5 here. So what happens when you plug -1 into the derivative? Well, looking down here, if you put -1 in, you get -1 times -1 minus 4 is just -5. -1 times -5 is just 5, so it's going to be positive. Plug in 2, you're going to get 2 times 2 minus 4 is -2. It's going to be negative. And then plug in 5, you're going to get 5 times 5 minus 4 is 1, so it's going to be positive again. So we have the function, the slope is positive before 0, so it's going to be increasing, increasing, increasing. It's going to go to 0, and then it's going to be negative after, so it's going to go back down. This means that we have a max at 0. If we look at 4, in 4's case, we're going down, 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 0, and then it's going to come back up. So that means we're going to have a minimum at x equal to 4. From there, we kind of know the general shape is going to look something like this, so we can assume it's local maximums, but for now, just say, there's going to be a local max at x equal to 0, and local max at x is equal to 4. And depending on the questions, sometimes they'll ask you for just where the maxes and mins occur, where local extrema occur, is kind of how they'll put it. In that case, you only need the x values, but if they say, what are the local extrema, then what you're going to want to do is just plug these numbers back into the original function. So if you were to put these back in, you would find that there's a relative max at, relative max of 15 at x is equal to 0, and there's a relative min of -17 at x is equal to 4. So that's pretty much all I wanted to cover today. Just remember to make those charts and just test those values, and it'll give you a really good insight on kind of what the function looks like. And just remember the signs have to flip, and the slope has to be equal to 0. Thanks for watching. I'll see you later.